Here we are going to learn about the series expansion of functions. Like you might have already seen the expansion of the function e raised to x as 1 plus x by 1 factorial plus x square by 2 factorial plus x cube by 3 factorial plus etc. And sin x as a series. Cos x also has a series expansion like this. And 1 by 1 minus x has the series expansion called a geometric series. This is called geometric series, which is 1 plus x square plus x cube plus etc. And you might have seen this as the infinite sum of a geometric progression whose first term is 1 and common ratio is x. So the question is, how are we writing functions as a series like this? And what are the conditions required for writing that function as a series, and how to find the coefficients, what are the uses of this series expansions. This is what we are going to see here. The above expansions of functions were a part of these special cases of Taylor series expansions of functions. Now suppose f is a real valued function which is differentiable infinitely many times in the neighborhood of a point x naught. So f is a function defined from some domain like a, b to r, and suppose that f is differentiable at a point x naught, and it is also differentiable in a neighborhood of the point x naught. That is, the function is differentiable in a neighborhood like x naught minus delta, x naught plus delta, where delta is a very small positive, small or big, whatever. Delta is a positive number. Okay, so this is a symmetric neighborhood of delta. That is, x naught from x naught towards right side we take delta distance, and towards left side we take delta distance. So that neighborhood is considered, and the function must be a differentiable infinite number of times in this neighborhood. Then if you take any point inside this neighborhood, we can write f of x as f of x naught, the values of uh, the function as well as its derivative at the point x naught. That is, we are writing f of x as f of x naught plus f dash x naught by 1 factorial into x minus x naught plus f double dash x naught by 2 factorial into x minus x naught whole square plus etc. plus the nth term will, sorry, n plus 1th derivative term will be nth derivative at x naught divided by n factorial into x minus x naught raised to n plus etc. So this kind of an expansion is called the Taylor series expansion of this function f of x about the point x naught. So the only condition is that f should be differentiable in a neighborhood of x naught of radius say delta. Then this expansion is valid for all those x inside this neighborhood. For example, if you consider the value x equal to 2 here, then the left side becomes 1 by 1 minus 2, which is a negative number, whereas the right side becomes 1 plus 2 square plus etc., which is positive infinity. So that's why this expansion is not valid if you take the modulus of the value xs greater than or equal to 1. It need not converge. So we have to study about the values of x for which the function can be represented as a series. That's also an aim of this. Now when x naught is equal to 0, this function, this series expansion takes a particular form, like f of x equal to f of 0 plus f dash 0 by 1 factorial into x plus f double dash 0 by 2 factorial into x square plus etc. Something like a standard polynomial. So that expansion, that is the Taylor series expansion at the point x naught equal to 0, is called a Maclaurin series expansion of f of x. So Maclaurin series expansion is nothing but the Taylor series expansion, whereas the point at which the expansion is done is the standard origin or 0. Okay, and you can see later that these are all parts of a special series called a power series expansions. And the expansions are valid in the symmetric interval x naught having the largest radius delta, such that the function becomes infinitely many times differentiable inside that neighborhood. And this expansion is coming from something called the Taylor's theorem, which we will see after this. So the use of this Taylor series expansions are in approximations of functions. And of course, many numerical analysis methods are making use of this Taylor series approximations. Now let us see the Taylor series expansions and Maclaurin series expansions of some functions which I've already discussed. For example, I consider the function f of x equal to e power x, and I'm going to find the Maclaurin series expansion. That means the Taylor series at 0 and the Taylor series at x equal to 3. So what are the things required as the derivatives of the function f of x? We need to calculate what is f of x, f dash x, f double dash x, etc. If possible, find the nth derivative of x also. And you need to know the values of the function at 0 for the Maclaurin series, that is f of 0, f dash 0, etc. And the value at 3, because we are going to evaluate the Taylor series at x equal to 3. So f of 3, f dash 3, f double dash 3, etc. So here all the derivatives are the same, e raised to x, and the value at 3 are all e raised to 3, and further at 0 these are e raised to 0, which is 1. So the Taylor series expansion of this particular function at 3 is f of x equal to e raised to x, which is equal to f of 0. F of 0 is e raised to 3 plus f dash 0 by 1 factorial, f dash 3 by 1 factorial, which is also e raised to 3 by 1 factorial into x minus 3 plus f double dash by 2 factorial into x minus 3 whole square plus etc. So this is the Taylor series expansion of this e raised to x at the point 3. And what about the Maclaurin series? It is just f of 0 plus f dash 0 by 1 factorial plus etc. So we'll have e raised to x is equal to 1 plus 1 by 1 factorial into x plus 1 by 2 factorial into x square plus 1 by 3 factorial into x cube plus etc. And you know that f of x is differentiable at every point. So the neighborhood can be taken as of infinite radius. That is, in the entire R, these expansions, these Taylor series expansions are valid for the function f of x equal to e power x because of its differentiability at each and every point. Now consider another function, that is f of x equal to 1 by 1 minus x, and let us calculate the Taylor series at x equal to 3 and its Maclaurin series. So I write 1 by 1 minus x as 1 minus x raised to minus 1. So f dash x becomes minus 1 into 1 minus x raised to minus 2 into minus 1. So minus 1 into minus 1 becomes plus 1. So f dash x equal to 1 into 1 minus x raised to minus 2. F double dash x will be 1 into minus 2 into 1 minus x raised to minus 3 into minus 1. So it becomes a positive coefficient. So 2 factorial into 1 minus x raised to minus 3, etc. The nth derivative is in this fashion. If you calculate, the third derivative is going to be 3 factorial into 1 minus x raised to minus 4, etc. Nth derivative is n factorial into 1 minus x raised to minus of n plus 1. Now evaluate the function values and its derivatives at the point 3 as well as 0, because you need the Maclaurin series as well as the Taylor series at x equal to 3. And the Maclaurin series is just 1 by 1 minus x is equal to 1 plus x square plus x cube plus etc., because this factorial notations will get cancelled, because f dash for example f double dash 0 is 2 factorial, so f double dash 0 by 2 factorial will be 1. So the first series, that is, this series is valid in the interval 1 comma 5, and the second series is valid in the interval minus 1 comma 1. Let us see how that comes. So if you observe, you can see that f of x equal to 1 by 1 minus x, we are going to expand about x equal to 3, and its non-differentiable point is 1, because the numerator is differentiable, denominator is a polynomial, it's also differentiable. So the function's differentiability is lost at the point x equal to 1. So this is the point at which, it's the only point at which the function is not differentiable. So if you are taking the point 3, we are expanding about 3. So the nearest non-differentiable point is 1. So you need to consider an interval which contains 3 as the center, and the neighborhood should not contain 1, because at 1 it loses its differentiability. So what I do is I'll consider the distance here. The distance is 2, 2, right? So to left side I will go to till 2, not including 2. So it should be an open interval. So right side, so this endpoint it will be 1, and to the right side also I take 2 distance. So this has to be 4, 5. So in the interval 1 comma 5, this expansion is valid. That means in the interval, if you take x belongs to the interval 1 comma 5, then you can write 1 by 1 minus x as the series which we have seen. That is 1 by 1 minus x can be written as this series. Now what about the Maclaurin series expansion? What about the validity of the Maclaurin series expansion? So Maclaurin series means we are expanding the function at the point 0. So we are expanding at the 0, so the same function, and its non-differentiable point is happening at 1. So the distance that you can take to the delta that you can take is one distance. So strictly not including 1. So it's an open interval. So to this side it should be 1, and to the left side also it should be a symmetric one. So minus 1. So inside the interval minus 1 comma 1, if you take any x, you can write 1 by 1 minus x as the Maclaurin series. That is this particular series. If you take any point outside the interval minus 1 1, this series expansion will not make any sense. So if you put x equal to 2, the left side becomes negative and right side become positive, and so they cannot be equal. So inside this interval minus 1 1, this expansion is valid. And if you take any x in 1 comma 5, the first series expansion is valid. We will see that the Taylor series expansion is coming from the Taylor's theorem, which tells you that a function f which is differentiable n times can be written as a finite sum. And in the finite sum, it looks like the Taylor series expansion, the first n minus 1 terms, and the nth term, it becomes very small. If you make n as say 1 lakh or 1 crore, the right side becomes very small and it goes to 0. So the limiting case, what happens is f of x will be equal to a series of the previous form. This we will see in the next